Hi everyone, this is Anderson Kanju and welcome back. So today we're diving into an exciting project where we'll explore a hard to see dataset using Python. So let's break down the code step by step. As always, our first step is to import all the necessary libraries that we need through the code so that we don't keep importing them again in between the codes. So we have Pandas, we have NumPy, we have Matplotlib and Seaborn. Plotly and Plotly is basically used for creating interactive visualization, because when you create a bar graph for a pie chart, you may want to know what percentage of, or what percentage is this fraction of the, is the proportion of the pie chart equal to, or for the bar you may want to know what value does this bar represent. So Plotly is very good for creating interactive plots. And then you use Scikit-learn. This is for now model building and machine learning. So next we load our dataset. The dataset was obtained from Kaggle, and as well as if you go to Kaggle and look for this as class Talang Hungary Final CSV, you'll find it. It also has the data dictionary where you can find the description for each variable. So next we view the head of the dataset. This is to ensure that the dataset we have indeed loaded is the one you're supposed to use. So you have to check it, and we just have an overview of how it is. Next we look for the missing values, so that when we start our analysis we should have already gathered for the missing values. I also checked for the data type so that I can be sure that I am working with integer data types or float data types, so that because those are the ones good, these are the ones used for statistical analysis. I also need to get the unique values. That's not a must, because I just want to know the unique values in each variable. So when you run this code, this is the output, the expected output. So from the imported dataset, we can see that in each variable there is no missing value. Sorry, and for the data types, age, all the variables apart from oil peak are integers, and oil peak is a float. So we're good to go to do our analysis. And then for the unique values, each has 50 unique values. Sex has 2 unique values, which is male, female, 0, 1, 0 representing female and 1 representing male, and so forth and so forth. Now we dive into our summary statistics. So this is where we look at the number of observation in each variable, which is the count, then the mean for each variable, the standard deviation, the minimum, and then the first quartile, the second quartile, which is also the median, and then the third quartile, and then the maximum value. From minimum all the way to max, this is what's called the five number summary statistics, if I'm not wrong. Yeah, for each variable. So maybe let's explore age. So we have 1190 entries for age. The mean is 53.72, which is approximately 54 years, and then the standard deviation is 9.35. The minimum value is 28. First quartile is 47, second quartile is 54, third quartile is 60, and then the maximum value is 77. Next, we plot distribution plots to see how our variables are distributed. So, okay, let's start from the first one. So we can see age is approximately normal. It's approximately normal. For sex, it's a categorical variable, so the only thing he can do is actually get to know how many are female, how many are male, so no need for the distribution. But I normally do this in case there are so many numerical variables, so you'll just do the distribution plot using the loop there, using the conditional statement at the loop, sorry. So For the chest pain type, it's as well a categorical variable. Then for the resting BPS, you can see it's approximately normal. It's approximately normal. Then the cholesterol as well, approximately normal. You can see approximately normal. Fasting blood sugar, categorical. Resting ECG, categorical. Maximum heart rate, approximately normal. No, not normal, but approximately normal. Exercise angina. Exercise angina is the type of chest pain, so it's also categorical. Then old peak, categorical. Then ST slope, it's uniform. Not sure whether it's categorical, but you can look into the data dictionary. Then the targets, which is a dependent variable for today, which is whether a person has a heart disease or not. It's categorical. Next, we explore the correlation between our variables using a correlation plot. So I can go, for instance, for age. So as always, the diagonal elements of our matrix will always be 1. This yellow diagonal matrix over here, because it's a variable in itself, as always. So let's explore age and all the other variables, or let's explore our dependent variable, which is target, with all the variables. So target and age correlation, a weak correlation, positive correlation 0.26. Then target and sex 0.3, target adjustment 0.4, targets and resting BPS 0.12. You see the good thing about Plotly, you can just hover over anywhere and you get your values very well. Then target and fasting blood sugar 0.21, target resting ECG 0.07, very weak. Maximum heart rate and target negative 0.4, target and exercise angina 0.48, target and oil peak 0.39, ST slope and target 0.5, and target and itself is 1. So we can see this is the highest correlation among target and ST slope. So I'm expecting to use ST slope in my logistic model. Next, I want to see the distribution of the target, or whether a person has disease, the distribution of you having a heart disease or not, depending on whether you're a male or a female. So let's go into the bar graph. Just leave the code. You don't have to understand the codes, all the codes over here. You just need to understand what do you want from this data set. This is what I want. If I'm given these variables, this is what I want. Don't worry about the codes. Don't worry about the codes. So if I come here and check and hover over here, again a very important aspect of Plotly. So if I come here, you can see that the number of female who did not have the heart disease were 211. The number of female who had heart disease was 70. The number of male who had heart disease was 350, and the number of male who had heart disease was 559. And from this, even without hovering around, you can see that the number of male is actually more than the number of female, and those who had heart disease for male is higher than those who had heart disease for female. And so from our data set, we can conclude that the number of males are actually more. From our data set, male are actually more than female. Then we go and check whether a person has heart disease, the distribution of you having a heart disease or not having heart disease, depending on whether you had angina or do not have angina. And again, I said angina is kind of chest pain. So those who had no angina, we can see that 483 did not have heart disease, and 246 had heart disease. 78 did not have, among those who had angina, 78 did not have heart disease, and 383 had heart disease. So it's very practical, because if you're having a chest pain, then it's likely that you have heart disease. So that's from the bar plot over here. So you can see that 246 who had no chest pain, no angina, had disease, and 383 who had angina had heart disease. Next, we now start the process of our modeling, and we need to select variables because we cannot work with all the variables. We cannot work with all the independent variables because we only have one dependent variable, which is target. So we cannot work with all independent variables. The reason being is some might not be predicting the dependent variable, which is target in this case, and some may be highly correlated. So today we're going to use a method known as backward elimination. This is whereby you start with all the variables and then eliminate one by one and see how your model will perform. So with this now I don't have to do that. I just come and use the stats model and then look at the p-values and look at the variables whose p-value is actually less than 0.05, and those will be the significant variables, and those whose p-value are actually greater than 0.05, then they won't be significant. So if I can leave alone the constant is leave alone the constant because it was not one of our variables. So we can see that age has a p-value of 0.08, which is greater than 0.05, and hence it's not significant. Sex is significant, chest pain type significant, and as I said, we look at the ST slope, it's 0, which means it is significant. Again, if we come and look at exercise angina, it's 0, which means it's significant. Next, we now fit our model. So fitting our model, we select the significant variables, where we select the variables which have a p-value of which have a p-value of 0.049 or less, so less than 0.05. Then we now split our dataset into the training and the test set, where training is where we teach our models, it's where we teach the machine how to understand our dataset. Now the test data is where we now test whether our model is accurate. So after fitting our model, now it's time to do the evaluation, and we do this using the metrics such as the precision, the recall, and the F1 score, as well as the accuracy. So from here we can see precision of 0.80 for those who do not have 0. This column over here, this one, the whole of these 0 represent those who do not have disease, and 1 represents those who had heart disease. So let's go to the precision. So for class 0, no heart disease, the precision is 0.80. This implies that 80% of the predictions that a person does not have disease are correct. Then we go for the precision of those who had heart disease, which is 0.84, which means that 84% of the prediction that a person has heart disease are correct. Then we go into the recall. We can see that those who did not have heart disease, there's a recall of 0.80, which implies that 80% of the actual cases, our model was able to identify them correctly where a person does not have heart disease. And then for the recall of 0.83, whereby this implies that the model correctly identifies 83% of the actual cases where a person has heart disease. For the F1 score, it's just the average, so 0.80. For the 0, it's just the average, so 0.80 per 0.00 divided by 2, 0.84. Just the average of the precision in the recall. Then for the support, we can see for those who did not have disease, 160, so they are 160 in success. And then For those who had heart disease, there are 197 instances. For the accuracy, macro average 0.82, it just goes without looking into the precision, the F1. It's calculated independently for each class, but rated by the number of instances of each class. Then we go to the confusion matrix, where we see the true positives, the false positives, and the false negatives and the true negatives. So for our case here, these are the true negatives. So we go with 0, 0. So they are the true negatives. That is 128 cases where the model correctly predicted no heart disease. And then these are the false. Where are we? These are the false negatives, where the model incorrectly predicted. They're the false negatives. Yeah. This is yes, no, yes, no, yes, no, no, yes, no, yes. Oh, these are the false positives, whereby these are the cases where they these are the false positives. So where the model incorrectly predicted heart disease, 33 are the false negatives, where the model incorrectly predicted no heart disease. So they said the person had heart disease where the person did not have, so it's correctly predicted no heart disease. And then these are the true positives, whereby the model correctly predicted the heart disease. So in summary, from this we can say approximately, from this over here we can say approximately 82% model 82% accuracy, which means that our model is approximately 82% accurate. So thank you for watching this video. See you in the next one.